Welcome to the deep dive. Today, we're putting on our learning hats, really, for a crucial topic, understanding how we measure effectiveness in parallel programming.
Yeah, it's super important.
If you've ever felt lost trying to figure out if running your code on multiple cores is actually, paying off, you're definitely in the right place.
Absolutely.
Our mission today is to extract the essential ideas around speed up and efficiency. Think of this as your personal audio study guide. We want to help you navigate this really important area.
Exactly. And we've gathered, well, different angles on this. We'll look from the ultimate theoretical limits of performance right down to the practical realities of making concurrent code work well, especially in .NET.
Right.
The aim is to give you a clear path through the core concepts without getting totally lost in the weeds.
Okay, perfect. So let's break down our study plan. We're tackling three key areas. First, those theoretical snags on speed, like what are the best possible gains we can expect? We'll look at Amdahl's and Gustafson's laws.
Big two, yeah.
Then we'll explore the work span model. That sounds like a more detailed way to think about performance when tasks can't be perfectly divided up.
It gets into the dependencies, yeah.
And finally, we'll look at the practical side, how synchronization works in .NET and why it's so essential. Sound good? Ready to dive in?
Absolutely. Let's start with those theoretical speed limits. They're fundamental, really, to understanding what's even possible.
Okay.
When we talk about measuring how well our parallel programs perform, the first things, the absolute basics to define, are speed up and efficiency.
Right. Speed up and efficiency.
Speed up is simply how much faster our program runs with multiple processors compared to just one. So mathematically, it's the time on one processor, let's call it T1, divided by the time on P processors, TP.
T1 over TP. Got it.
And then efficiency tells us how well we're actually using those processors. That's calculated as the speed up,
Yeah.
SP divided by the number of processors, P.
Okay. So speed up is the faster number we want, and efficiency tells us if we're being smart about using all that power. Makes sense. Now, a cornerstone here is Amdahl's law. What's the core insight we need to grab from this for our study guide?
Okay, Amdahl's law. The crucial idea, the thing to really remember, is that when you have a fixed amount of work and you try to speed it up with more processors, the part of your program that cannot be parallelized, that part will ultimately limit how much faster you can go.
Right.
No matter how many processors you throw at it, it's a fundamental bottleneck.
So even if, say, 99% of my code can run in parallel, that tiny 1% that has to run step by step will hold everything back eventually.
Exactly.
Like that superhighway merging into a single lane, the bottleneck is just inevitable.
Precisely. Let's use a bit of notation. Say sigma represents the proportion of the total single processor time, T1, that is inherently serial code, stuff that just has to run sequentially.
Okay, sigma is the serial fraction.
Then 1 is the part that can be parallelized. Amdahl's law gives us an upper limit, a ceiling, on the speed up. SP is less than or equal to 1 divided by plus 1p, where p is the number of processors.
Okay, that formula looks a bit technical, but the key for our study guide, it seems, is what happens as p, the number of processors, gets really, really big. That 1 minus divided by p part,
Yeah,
it gets closer and closer to 0.
exactly. You got it. And here's where it gets really interesting for understanding the limits. As p approaches infinity, that parallelizable portion's impact just fades away.
Right.
And Amdahl's law tells us the speed up will be limited to 1 divided by psi.
Wow.
So, the brutal truth is, even if you have near-perfect parallelization, it can still be crippled by that stubborn serial sliver of code.
So if, say, 10% of my program is serial, is 0.1, the absolute best speed up I could ever hope for, even with 1 million processors, is 1 divided by 0.1, which is 10 times faster.
That's it, just 10x.
That's a serious reality check if you were dreaming of hundreds or thousands of times faster performance.
It is indeed, and it underscores a key takeaway for our study guide. Amdahl's law assumes we're working with the same fixed problem. It strongly favors problems that can be broken down into completely independent parts, what we call embarrassingly parallel.
Embarrassingly parallel.
And, crucially, there's always an ultimate speed limit imposed by that serial fraction, no matter how much parallel power you throw at it.
Okay.
Remember that example of 5 friends painting a house? If one room needs a really intricate single-person job that takes ages, the overall painting time will always be significantly affected by that one slow task. Even if the other rooms get painted super fast in parallel, that intricate job, that's our serial portion.
That paints a clear picture. Okay, fixed problem, favor independent tasks, serial part is the ultimate drag. Got it for Amdahl. Now let's look at Gustafson's law. You said it offers a slightly more optimistic view.
Yes, it shifts the perspective quite a bit.
What's the core shift here for our study guide?
The key difference with Gustafson's law is that it recognizes something important about how we actually use computers. When we get more computing power, we often don't just solve the same problems faster. We
Hmm.
tend to tackle much larger, more complex problems.
Ah, right. So instead of assuming a fixed workload, Gustafson's law considers how much more work we can do in the same amount of parallel time as we increase the number of processors.
Exactly. As our computers get stronger, we don't just speed up the old stuff. We take on bigger challenges.
It's like getting a faster car and deciding, okay, now I can drive across the country instead of just, going around the block faster.
Perfect analogy. Gustafson's law suggests that as the total workload we're handling in parallel grows, the impact of the serial portion can become less significant relative to the overall increased work.
Okay, so how does this change the way we think about speed up for our study guide notes?
Well, let's use slightly different notation. Say S is the fraction of the parallel runtime that's spent doing serial work, and Q, which is 1/earth, is the fraction spent doing parallel work across P processors.
Okay, S and Q in the parallel context.
Gustafson's law gives us the scaled speedup as S plus Q multiplied by P. You can also write as P plus 1P multiplied by S.
So instead of being limited by the serial part of the original smaller problem, we're looking at the serial part within the now larger parallelized effort. And what happens to our potential speed up as we keep adding processors in this scenario?
This is the optimistic part. If
Hmm.
we assume that S, the proportion in serial work within our scaled parallel execution, remains relatively constant, even as we increase the problem size and the number of processors,
Yeah.
then the speedup, which is S plus 1S, will also increase, potentially without a fixed upper limit like Amdahl's.
Whoa.
It's a much more optimistic outlook, right?
Hmm.
While Amdahl gave us that hard stop, Gustafson suggests the possibility of continued gains, provided we scale the problem size along with the processors.
That's a huge difference in mindset. It's like Amdahl's law says, here's the wall you'll hit. But Gustafson's law says, hey, if you take on a big enough job, more hands will keep making it proportionally faster.
Precisely. And this highlights the different underlying assumptions. Amdahl's law, let's call it the glass half empty view for our study guide, focuses on a fixed problem.
Right.
Gustafson's law, the glass half full view, recognizes that we often leverage increased computing power to solve bigger problems.
So the crucial question for us as learners is, are we trying to make a specific, unchanging task run faster? Or are we aiming to tackle a much larger, more complex task within a reasonable time frame?
That's the key distinction. Same task faster versus bigger task in similar time. You nailed it.
Got it. So Amdahl and Gustafson give us these, well, best case theoretical scenarios. But what about the real world? What are some factors that stop us from actually reaching these ideal speedups in our parallel programs?
Ah, yes, overhead. In practice, we almost always encounter overhead.
A hidden cost?
Exactly. Things like the time it takes just to create and manage threads. The need for threads to coordinate and share data, that's synchronization, which takes time. And also load imbalance, where some processors might be working hard while others are just sitting idle.
Right.
All these overheads eat into the potential speedup we calculated with the laws.
Okay, overhead the practical drag. So we have the theory, the costs. Now let's move on to the work span model. This sounds like it gives us a more detailed way to analyze performance for our study guide.
It does. The workspan model goes beyond just dividing work into serial and parallel. It looks at how the individual tasks within a program actually depend on each other.
Dependencies, okay.
It uses something called a directed acyclic graph, or DAG.
Yeah.
Think of it like a flowchart where the nodes are tasks and the arrows show which tasks must finish before others can start.
Like a recipe. You can't bake the cake before you mix the ingredients.
Exactly like a recipe.
Yeah.
So instead of just saying this percentage is parallel, we're actually mapping out the flow of execution and what has to happen in sequence.
Makes sense?
Within this model, we define two key terms for our study guide: work and span. Work, often written as T1, is the total amount of computation needed, basically, the time it would take to do everything sequentially on just one processor.
T1, total work. Got it.
Span, often written as TIL, T infinity, is the length of the longest chain of dependent tasks in that DAG. This represents the minimum time the program could possibly take, even if you had infinite processors.
Why infinite?
Because those tasks in the longest chain have to happen one after the other due to dependencies. You can't speed up that chain itself beyond doing one step at a time. That longest sequence is often the real bottleneck.
Okay, so the span is another kind of fundamental limit, but this one's based on the inherent dependencies in our algorithm, not just the serial fraction.
Precisely. And the work span model gives us an upper bound on speedup based on this. Speedup, SP, is less than or equal to work divided by span, SP T1 2y.
Work over span.
This bound is often tighter or more accurate than Amdahl's law because it directly considers the limitations imposed by those task dependencies.
That makes intuitive sense for our study guide. If I have a long string of tasks that absolutely must be done in order, no amount of extra processors can speed up that specific chain.
Exactly.
Yeah.
Now, a really crucial result from the work span model is Brent's lemma. It gives us an idea of the actual parallel execution time, TP, when we have a limited number, P, of processors. It states that T1P is less than or equal to TP,
Okay.
which is less than or equal to T1P plus TP.
Right. Another formula for the notes. But what's the practical takeaway? What does this mean for our study guide?
Well, one key point is that if the span T is much, much smaller than the total work, P1, then T1P becomes a pretty reasonable estimate for the parallel runtime.
Ah, okay.
This suggests we can get close to ideal speed up. In that case, like
Yeah.
doubling processors might roughly have the time. However, the lemma also really emphasizes that the span sets a fundamental limit on how much we can speed things up no matter how many processors we have. We'll never go faster than the longest chain of dependencies allows.
So for our study guide, when we're designing parallel algorithms, a major goal should be to shorten that critical path, that longest sequence of dependent steps. We want to make TU smaller.
Absolutely. That's often where the biggest gains come from algorithmically. Consider adding n numbers again.
Okay.
A simple serial loop takes n steps. So work, T1, and span, TR, are both basically n. But if we use a parallel approach, like adding pairs of numbers at each step in a tree structure,
Like a tournament bracket.
exactly, we could reduce the span to roughly log base 2 of n. That's a huge reduction in span. This shows how redesigning the algorithm can dramatically improve the potential for parallel speedup by shrinking tissue.
That's a great example for our study guide. Algorithm choice is critical for reducing that dependency bottleneck. Now, I also saw parallel slack and burden span mentioned in the sources. Quick definitions for our understanding.
Sure. Parallel slack is essentially a measure of how much potential parallelism we have compared to our resources.
Mm.
It's often calculated as T1, BTQA. A high parallel slack generally means we have plenty of parallel work available for our processors, which can help with load balancing.
More work than needed, kind of.
Yeah, enough work to keep everyone busy. Burden span is just the span, but acknowledging the real-world overheads. It's the span plus the time costs of synchronization and communication between those dependent tasks. In real systems, following those dependency arrows isn't free. It costs time.
Gotcha. So, recap for the study guide. Workspan uses DAGs for dependencies. It provides bounds on speedup, T1 T-SHA. It usually assumes things like a good task scheduler and enough memory bandwidth. The span is key for scalability, and maybe, counterintuitively, sometimes increasing the total work T1 a bit can actually reduce the span and be beneficial overall.
You've got it. That's a good summary.
Okay, now let's shift gears. Let's get practical and talk about the world of .NET and how we actually make parallel programs work correctly. Let's talk synchronization. Why is this so crucial?
It's crucial because when you have multiple threads running at the same time, maybe accessing and changing the same data like a shared counter or
Yeah.
list, you need rules. You need traffic control.
Right.
Without synchronization, threads can interfere with each other in unpredictable ways, leading to corrupted data and incorrect results. These are often called race conditions.
We need traffic laws for our concurrent threads to avoid, well, crashes and gridlock. So what are the fundamental concepts of concurrency and parallelism we need in our .NET study guide? Any key distinctions?
Yeah, it's helpful to be clear on the terms. Sequential is just one thing after another. Concurrent means multiple things seem to happen at the same time, maybe by quickly switching between tasks.
Yeah.
Parallel means multiple things are actually happening simultaneously, usually on different CPU cores.
Okay, sequential, concurrent, parallel.
And we also distinguish between processes and threads. Processes have their own isolated memory spaces safer, but switching between them is slower. Threads live within a process and share memory faster switching, but that shared memory is where the danger lies.
That shared memory.
Exactly.
Sure.
That's what creates the need for careful synchronization. Also, a key characteristic of concurrent programs is that they're often non-deterministic. The exact order of operations can change slightly each time you run it.
Which makes debugging a nightmare, right?
So absolutely. Bugs might appear only sometimes, making them incredibly hard to find and fix.
So synchronization is the set of tools and techniques we use to bring some order, some predictability to this potentially chaotic world of concurrent threads. What are the basic models or approaches?
The two main models are shared memory synchronization and message passing. With shared memory, which is common in .NET threading, threads communicate kind of implicitly by reading and writing to the same memory
Like
locations.
a shared whiteboard.
Good analogy. It's often fast, but you need explicit protection mechanisms like locks or mutexes to make sure only one thread writes to the whiteboard at a time, or that reads, see consistent data.
Okay. And message passing.
Message passing involves explicit communication. Threads send discrete messages or data packets to each other. Think of it like sending emails or letters. It can be inherently safer because data isn't directly shared, but there might be more overhead involved in sending and receiving messages.
Shared memory. Shared whiteboard. Need rules. Message passing. Sending notes. Maybe slower but clearer boundaries. Makes sense for our study guide. Now, what about common mistakes? What are some pitfalls we should really watch out for in concurrent programming?
There are a few classic bug patterns, atomicity violations. That's when a sequence of operations that you assume will happen indivisibly, like read, modify, write, gets interrupted by another thread partway through. Order violations. Things happen in the wrong sequence. Maybe thread A needs data prepared by thread B, but A gets there first. And just generally making wrong assumptions about timing or how threads will interleave.
So it's not just about preventing crashes, it's about ensuring the logic remains correct even when things happen concurrently. What are the key properties we're actually aiming for when we write concurrent code?
We generally aim for four things. Safety. The program behaves correctly, data remains consistent, no corruption. Liveness. The program makes progress. Threads don't get stuck forever in deadlocks or keep waiting indefinitely, which is starvation.
Safety and liveness. Okay.
Determinism is often desirable, meaning the program gives the same result for the same input every time, though this can be hard to achieve in highly concurrent systems.
Yeah.
And finally, we need to be mindful of overhead, the performance cost associated with threading and synchronization itself. Too much overhead can negate the benefits of parallelism.
Right. Safety, liveness, maybe determinism, and watch the overhead. We also hear about data races a lot. How do those fit in for our study guide?
A data race is a specific type of safety problem. It happens when you have two or more threads accessing the same memory location concurrently, and at least one of those accesses is a write, and there's no synchronization mechanism like a lock coordinating those accesses.
So multiple threads, same memory, one writes, no lock equals data race.
Exactly. And data races are a primary cause of those unpredictable behaviors we call race conditions.
And those really dreaded deadlocks where everything just grinds to a halt because threads are stuck waiting for each other. What's the recipe for a deadlock in our study guide? How do they happen?
Deadlocks typically require four conditions to hold simultaneously. These are often called the Kaufman conditions. First, mutual exclusion. Resources involved can't be shared. They can only be used by one thread at a time.
Okay, one thread per resource.
Second, hold and wait. A thread is holding at least one resource and is waiting to acquire additional resources held by other threads.
Holding one, waiting for another.
Third, no preemption. Resources cannot be forcibly taken away from a thread. They can only be released voluntarily by the thread holding them.
Can't steal resources.
And fourth, circular wait. There exists a set of waiting threads where thread A is waiting for a resource held by thread B is waiting for thread C, and so on, until some thread Z is waiting for a resource held by thread A, forming a circle.
A cycle of waiting. Wow. All four need to happen.
Yep. If you can break just one of these conditions, you can prevent deadlocks.
Okay, that's the theory of what can go wrong. Now let's get practical again. What tools does .NET actually give us in our synchronization toolkit? What's in the box?
.NET provides a really rich set of synchronization primitives, mostly found in the system. Threading namespace. Many of these are actually built upon a base class called waitHandle.
waitHandle, okay.
Let's start with the absolute basics, the thread class itself. This lets you explicitly create and manage individual threads. You can start them, you can pause them using sleep, though usually not recommended for synchronization, and you can wait for them to finish using join.
Join waits for it to complete.
Right. And it's also key to understand the difference between background and foreground threads. Foreground threads keep the application alive until they finish. Background threads don't.
Okay. And then we have the thread pool. Why is that generally preferred for managing lots of tasks in .NET? What's the advantage for our study guide?
The thread pool is huge. It manages a pool of reusable background threads for you. This drastically reduces the overhead associated with creating and destroying threads, especially if you have many short-lived tasks. Creating a new thread isn't free.
So it reuses them.
Exactly. You can submit work using the older thread pool, queue user work item method, or more commonly these days using task. Run from the task parallel library or TPL. The TPL often uses the thread pool behind the scenes.
So the thread pool is like having a ready workforce on standby, saving us the cost of hiring and firing individual workers for every small job. Smart. Now, for controlling access to shared resources, we have mutex and semaphore. What's the key difference to note down?
Good question. A mutex, which stands for mutual exclusion, is designed to grant exclusive access to a resource. Only one thread can own or hold the mutex at any given time. It's like having a single key to a critical room.
One key only. Mutex.
A semaphore, on the other hand, limits the number of threads that can access a resource or a pool of resources concurrently up to a certain maximum count. It's like having a limited number of keys, say 5 keys, to a room. Yep. Up to 5 threads can enter.
Okay, single key for mutex, limited number of keys account for semaphore. Got it. What about signaling between threads? We have event wait handle and specifically auto reset event and manual reset event. How do these help coordination in our study guide?
These are primarily for signaling. They allow one thread to signal an event to one or more other threads that might be waiting for that event. An auto reset event is like a turnstile or a gate that lets exactly one waiting thread through when it's signaled, and then it automatically resets, closing the gate again.
Just one gets through. Auto.
A manual reset event is more like a gate that, when signaled opened, stays open, letting all waiting threads through and any threads that arrive while it's open until someone explicitly calls its reset method to close the gate again.
Stays open until manually closed. Manual. Got it. What about monitor and the lock keyword in C#? They seem super common for protecting code blocks.
They are extremely common, especially lock. The monitor class provides the underlying mechanisms for acquiring and releasing an exclusive lock on an object. The lock keyword in C# is essentially syntactic sugar, a shortcut for using monitor.enter and monitor.exit in a try.finally block.
Ah, so lock makes it safer.
Yes, it guarantees that the lock is always released, even if an exception occurs within the locked code block, which is crucial to prevent deadlocks. Monitor also offers more advanced features like wait, pulse, and pulseall for more complex condition variable patterns, where threads wait inside the lock for a specific condition to become true.
Okay, lock is the easy, safe way for basic mutual exclusion. Now, reader-writer lock sum sounds pretty specific. What's its niche for our study guide?
Its niche is optimizing scenarios where you have many threads that need to read a shared resource, but only occasionally does a thread need to write to it.
Read-heavy situations.
Exactly. It allows multiple threads to acquire read locks simultaneously, letting them all read concurrently. But when a thread wants to write, it must acquire an exclusive write lock, which blocks all other readers and writers. This can significantly improve performance compared to a simple lock if reads are far more common than writes.
That makes perfect sense. Let many read together, but make writers wait and have exclusive access. We're really building up our .NET toolkit here. Okay, quickly. We also have spin lock, countdown event, barrier, and timer. Quick takeaways for the study guide.
Okay, rapid fire. Spin lock, a low-level lock. Instead of putting the thread to sleep when waiting, it just keeps checking the lock in a tight loop. It's only efficient for very, very short lock hold times where the contention is expected to be low. Otherwise, it wastes CPU cycles.
Spin lock for tiny waits.
Countdown event. Super useful. You initialize it with a count. Threads signal the event, decrementing the count. You can have another thread wait until the count reaches 0. Great for fork join scenarios where you start several tasks and need to wait for all of them to finish.
Wait for n things to complete. Countdown event.
Barrier. Synchronizes multiple threads at a specific point in their execution. All participating threads wait at the barrier until all threads have reached it. Then they all proceed together. Useful for phase computations where each phase depends on the previous one being complete across all threads.
Roll me here, then go. Barrier.
Timer. Allows you to schedule a method to execute on a thread pool thread at regular intervals or after certain delay. Just be careful using timers that update UI elements you usually need to marshal the callback to the UI thread.
Timed execution and cancellation token.
Ah, yes. Crucial for responsiveness. Cancellation token provides a standard cooperative way for you to signal to a long-running task that it should stop its work gracefully. The task needs to periodically check the token to see if cancellation has been requested.
Cooperative stopping. Got it. Wow, that's a comprehensive toolkit. Choosing the right tool clearly depends heavily on the specific synchronization problem you're trying to solve.
Absolutely. There's no one-size-fits-all.
Now, to really nail these concepts for our study guide, let's look at a practical example they used. Parallel summation in .NET.
Right, this is a classic example. It ties together the performance concepts and the synchronization tools nicely. The goal is simple. Add up all the numbers in a potentially large array, but do it faster using parallel processing. Often, the approach involves a kind of binary tree reduction.
So instead of just one thread going 1 plus 2 plus 3 plus 4, we have multiple threads adding pairs, then pairs of those sums, and so on, reducing the work logarithmically.
Exactly. The source material we looked at provided several C# examples showing different ways to implement this. They started with a naive approach, just creating lots and lots of individual thread objects.
Which we now know has high overhead.
Right. Then they showed how to limit the degree of parallelism using semaphore slim, a lighter weight semaphore. They demonstrated joining the threads or coordinating the summation levels using countdown event and also barrier.
Applying those tools we just discussed.
Exactly. And finally, they showed more efficient approaches using the thread pool directly and also using task, run from the task parallel library, which is often the recommended modern approach.
And they even had benchmark results, right? Comparing how these different methods actually performed against the theoretical expectations, like Brent's lemma. What were the key lessons for our study guide from those numbers?
The benchmarks really drove home the point about the overhead of excessive thread creation. The naive thread approach was often slow. The thread pool and TPL, task run, generally offered much better performance due to thread reuse and the system's ability to manage concurrency effectively.
Okay, reuse helps.
And techniques like limiting concurrency with semaphore when appropriate and using tools like countdown event for coordinating the stages of the summation also proved effective in structuring the parallel work. It reinforces the idea that choosing the right concurrency patterns and carefully managing the degree of parallelism are vital for getting good performance. You don't always want maximum possible parallelism.
It's great to see the theory, like overhead and span, connecting directly to real-world performance in those benchmarks. Excellent for the study guide. Now, let's quickly touch on one more classic concurrency problem. The bounded buffer, also known as the producer-consumer problem.
Yes, another fundamental pattern. You have one or more producer threads that generate data and put it into a shared buffer, like a queue or array. And you have one or more consumer threads that take data out of the buffer and process it.
Producers make, consumers take.
Right. And the buffer typically has a limited size, hence bounded. The main synchronization challenge is this. Producers shouldn't try to add data to a buffer that's already full, and consumers shouldn't try to take data from a buffer that's currently empty.
So we need to manage the not full condition for producers and the not empty condition for consumers. That's the core task for our study guide here.
Exactly. The source material showed a couple of ways to handle this. First, a really inefficient approach using busy waiting, where threads just spin in a loop, checking the condition.
Wasting CPU.
Definitely avoid that if possible. Then a much better solution using two semaphore objects. One semaphore could track the number of empty slots available in the buffer, signaling producers when space is available. The other could track the number of items currently in the buffer, signaling consumers when items are available.
Two semaphores, one for space, one for items. Clever.
Yeah. And additionally, you still need a lock, like using monitor the lock keyword, to protect the actual buffer itself during the moments when a producer is adding an item or a consumer is removing one, to prevent data races on the buffer's internal structure.
So the semaphores manage the waiting for space or items, and the lock ensures only one thread physically touches the buffer data structure at any instant. Key takeaways for the study guide there.
Precisely. The source also briefly touched on unbounded buffers, where the full condition isn't an issue, and how producers might signal to consumers that they're finished producing data, perhaps by putting a special end marker item into the buffer.
A poison pill, sometimes called.
Right. And it also gave a neat little example of an unbounded task queue using semaphore slim to signal available work to a dedicated background worker thread.
These examples really help solidify how these different synchronization tools are actually used to solve common concurrency problems. Very valuable for the study guide.
They do. And hopefully this whole deep dive has served as a valuable audio study guide for you. We aim to give you a strong foundation in understanding how to measure performance in parallel programming, looking at the theoretical limits with Amdahl's and Gustafson's laws.
Right. The ceiling.
And getting more detailed with the workspan model and dependencies.
T1 over T infinity.
And finally, covering the practical synchronization tools and patterns available in .NET.
Absolutely. Understanding these trade-offs, knowing the difference between a mutex and a semaphore, when to use a barrier versus a countdown event, it's so important for writing parallel code that's not just fast, but also correct and efficient.
Couldn't agree more.
So as a final thought, maybe something to really solidify your learning from this study guide session. Considering the benchmark results we discussed and those theoretical models like Andal's, Gustafson's, and Workspan, what do you think are the most critical strategies for achieving good parallel performance in real-world applications? And maybe more importantly, how might the specific nature of the workload, is it CPU-bound, I/O-bound, fixed size, scalable, influence the choices you make?
That's a great question to ponder.
It's a crucial question, really, as you continue exploring this area. Remember, this was a foundational look. There's always much more nuance and depth to explore in parallel and concurrent programming. Thanks for joining us on this deep dive.